In just 1 year from now, a space station designed to replace the ISS will lift off into orbit. And we're talking about Haven 1, an incredibly advanced space station module developed by VAST. This isn't just another experiment. Haven 1 is poised to shatter growing concerns that China could dominate Earth orbit with its Tiangong space station. And of course, a bold vision like this wouldn't be possible without a major contribution from SpaceX. So, how far along is Haven 1 right now? And more importantly, how could it redefine the standards of space station design in the years ahead? Let's find out in today's episode of Alpha Tech. The era of the International Space Station is slowly coming to an end. NASA has officially planned to retire the ISS around 2030 after more than 3 decades of non-stop contributions to scientific research and international cooperation. That leaves us with just over 4 years from now. Let me repeat that, just 4 years. And such a short timeline has created enormous pressure on NASA to find viable replacements that can keep humans continuously present in low Earth orbit. Against this backdrop, the commercial LEO Destinations program has turned into a fierce race involving major players like Axiom Space Voyager Technologies and Blue Origin. But when you look closely at real-world progress and long-term sustainability, one project clearly stands out. More than any other contender, Vast Space's Haven ecosystem appears to be the most realistic and capable successor to the ISS legacy. And now, for the first time in quite a while, Vast made a rare move by sharing a key milestone and an updated timeline on X, stating Haven 1 has begun the first phase of cleanroom integration at Vast HQ. With this milestone, we are updating the schedule for Haven 1 to be ready to launch in Q1 2027. At first glance, this sounds like good news, but almost immediately a serious issue stood out. The original plan called for a launch in mid-2026, meaning Haven 1 was supposed to reach orbit in just 5 or 6 months. Now that target has shifted to the first quarter of 2027. So, what happened? In an interview with Ars Technica Vast, CEO Max Hayat offered a clear and refreshingly realistic explanation for the delay. Hayat revealed that as of January 10th, 2026, the team had completed the entire primary structure and part of the secondary structure with acceptance testing already finished back in November 2025. Based on this real-world progress, the company realized that the remaining integration and final closeout work would likely run into the fall of 2026. That would then be followed by a full environmental test campaign at NASA's Plum Brook facility toward the end of the year, pushing the launch window into Q1 2027. He was careful to emphasize that this was not a delay caused by failures or unexpected technical problems. Instead, it was a schedule adjustment driven by a much deeper understanding of what it truly takes to build a flight-ready space station. Module, a highly complex process that demands absolute precision to ensure crew safety and long-term durability. Hayat added that the new timeline actually de-risks the entire program. The team now has a clear data-backed picture of how long each step really takes, rather than relying on earlier overly optimistic estimates. He also noted that the time between Haven 1's launch and the arrival of its first crew could range from a few weeks to several years, depending on the readiness of the module itself, Crew Dragon availability, and other system-level factors. But the priority is clear: get the module safely and stably into orbit first. In other words, better safe than sorry. At this point, Haven 1 has officially entered its first phase of clean room integration at VAST's headquarters. This is the stage where engineers begin installing the module's core service systems onto the completed primary structure, including pressure management, thermal control, life support, propulsion, and the associated fuel tanks. And take a look at the images that were released alongside the update. They show the massive cylindrical module inside a spacious clean room, surrounded by engineers in white protective suits working methodically around the structure. In the background, you can see a modern facility marked by the American flag and the VAST logo. It's a striking visual one that clearly signals a major transition. Haven 1 is moving beyond the era of standalone components and into full system-level assembly, laying the groundwork for comprehensive testing and, ultimately, a flight-ready space station module. Now, let's take a closer look. What exactly makes Haven 1 stand out? At its core, Haven 1 isn't just another commercial space station. It's a carefully engineered technological statement built around a minimum viable product philosophy, prioritizing speed safety and real-world operability over unnecessary complexity. In terms of size and mass, Haven 1 has a launch mass of 14,600 kilograms, with a diameter of 4.4 meters and a length of 10.1 meters. Its primary structure is monolithic, meaning it's welded as a single piece from aluminum panels. This allows it to fit perfectly inside Falcon 9's standard payload fairing, which is about 5.2 meters in diameter. That design choice has major implications. Haven 1 becomes the largest pressurized payload ever launched by Falcon 9, offering 80 cubic meters of pressurized volume and 45 cubic meters of habitable space. It achieves this without requiring an extended fairing or Falcon Heavy, by fully exploiting every centimeter of available fairing volume. A key turning point came in early 2024, when VAST switched from stainless steel to aluminum alloy 2219 after running parallel material tests. This wasn't a theoretical decision, it was driven by manufacturing reality. Aluminum is far more compatible with 5-axis CNC machining, significantly reducing production time and cost, while enabling highly precise orthogrid reinforcement structures. The result is a shell that can withstand launch loads and orbital pressure while remaining substantially lighter. But Haven 1's feasibility hinges on one critical factor: its tight integration with SpaceX. Rather than developing an entire life support ecosystem from scratch, VAST smartly leverages Crew Dragon as a functional support module. Dragon transports the crew, handles much of the initial life support load, and docks passively via an adapter designed by SpaceX, with fit checks already completed by late 2025. Even carbon dioxide removal follows this philosophy. Instead of manufacturing dozens of dedicated scrubbers, VAST relies on Dragon's proven CO2 cartridges, stocking only what's needed for short missions. Over Haven 1's 3-year lifespan, the plan calls for roughly 4 crewed missions, each lasting about 2 weeks, plus an initial uncrewed commissioning phase. This approach expands livable space by roughly 6 times compared to staying inside Dragon alone, transforming Haven 1 into a true orbital home, not just an extended capsule. Inside Haven, 1 clearly breaks from traditional space station design, with a human-centric layout. The centerpiece is a 1.1-meter domed window located in a 24 cubic meter common area. Unlike the ISS cupola, this is a single panoramic dome offering nearly 180 degrees of Earth views, complete with MMOD shielding and impact testing already completed. Sleeping quarters represent one of Haven 1's most novel innovations, currently patent pending. Each of the 4 private crew quarters features a queen-size sleeping surface with adjustable equalized pressure distribution. This design helps reduce the floating sensation in microgravity and supports both side sleeping and back sleeping, a significant upgrade over the suspended sleeping bags used on the ISS. Waste management is equally well thought out. Haven 1 uses 8 wet trash tanks, each capable of handling 5 days of waste for 4 crew members. These tanks are vacuum sealed and vented externally, preventing odor buildup and bacterial spread in the sealed habitat. On the control side, Haven 1 is equipped with 6 control moment gyroscopes, all designed and manufactured in-house by VAST. The current V3 generation, revealed in 2024, allows precise attitude control without expending propellant, critical for maintaining solar alignment. Power comes from 12 deployable solar arrays, delivering up to 13.2 kilowatts peak output. Most core components, including flight computers, batteries, pressure valves, and cold plates, have already been flight tested via Haven Demo, a 552-kilogram technology demonstrator launched successfully on SpaceX's Bandwagon 4 rideshare mission in November 2025. That mission validated propulsion, avionics, and power systems before committing them to the full flight article. Taken as a whole, Haven 1 is far more than the first commercial space station. It's a strategic technology platform, one that favors speed, safety, and real operational learning over chasing perfection on day one. But here's the real question. Why does Haven's design pose such a serious threat to its competitors in the race to replace the ISS? As we've touched on earlier, the first and perhaps smartest decision VAST made was choosing SpaceX as its core partner. Haven's docking ports are designed to be fully compatible with Crew Dragon, the primary vehicle for transporting crews to and from orbit. On top of that, Haven 1 deliberately leverages Dragon's life support systems to support longer duration missions rather than reinventing everything from scratch. What truly sets Haven 1 apart, however, is that it will be the first commercial space station equipped with a Starlink laser terminal. That means gigabit-class internet speeds with low latency in orbit, enabling high-quality video calls, real-time transmission of scientific data, and even Wi-Fi connectivity for personal devices on board. Combined with its clean, modern, minimalist interior design, Haven 1 doesn't feel like a traditional space station at all. It looks more like a luxury hotel room in orbit, the kind that would easily cost hundreds of thousands of dollars per night if space tourism pricing ever becomes the norm. This approach proves a crucial point. Partnering closely with a dominant launch and spacecraft provider like SpaceX can dramatically accelerate timelines and improve economic viability, especially when Falcon 9 has already demonstrated exceptional reliability at a relatively low cost. When you compare this to Axiom Station, one of Haven's primary competitors, the contrast in strategy becomes very clear. Axiom has pursued a fully modular approach, from the start building highly autonomous modules with their own propulsion and control systems. These modules are first attached to the ISS, then later separated to form an independent station, a design optimized for long-term expansion and continuous habitation. Haven 1, by contrast, takes a very different path. Start small, prove it works, then scale up. VAST has already completed docking fit check tests and moved directly into system integration. This dramatically reduces early complexity, shortens the time to an operational station currently targeted for 2027, potentially several months ahead of Axiom's schedule, and most importantly, generates real flight data. That data will feed directly into Haven 2, which is currently planned to launch in 2028. It will be an upgraded NASA-certified evolution of Haven 1. The diameter remains 4.4 meters, ensuring compatibility with Falcon Heavy, but the module is stretched by roughly 5 additional meters, bringing its total length to about 16 meters. That extra length nearly doubles the livable space, with a projected habitable volume of around 80 to 90 cubic meters for a single module. Recently, a man named Ben Longmire, one of the leading engineers in the satellite industry and a former senior figure at SpaceX, stepped away from the company due to family reasons after years of truly remarkable contributions. He was the person who led the development of direct-to-cell, or DTC, a breakthrough technology that allows ordinary smartphones to connect directly to satellites with no additional hardware required. Today, that system has already been deployed across thousands of satellites serving users on 6 continents. And yet, even after leaving SpaceX, Ben Longmire publicly thanked both Elon Musk and Gwynne Shotwell. More importantly, he made it clear that SpaceX's journey is far from over, stating, "Obviously, this is only the beginning for SpaceX as Elon and the team continue to expand humanity's presence to the Moon, Mars, and further along the Kardashev scale." In other words, someone with his level of talent and experience openly aligned himself with a vision many still dismiss as science fiction. For a moment, it almost seemed like Elon Musk had set that dream aside, focusing instead on nearer-term goals, like building an AI data center in orbit or establishing satellite manufacturing facilities on the Moon. But then just recently, Musk dropped a post that sent shockwaves through the space community. "Don't want to get complacent, but if civilization keeps advancing, humans will reach Mars in 5 to 10 years. What really matters is building a self-sustaining civilization on Mars, which will take another 20 to 30 years. And yes, when Musk talks about civilization, he may very well be referring to SpaceX itself, because right now, it's the only company on Earth actively designing a true Mars landing system, Starship. Everyone else is still talking about rovers and orbital probes. Starship is about people. Starship is the largest, most powerful, and most ambitious launch vehicle humanity has ever built. This is not just another rocket. It's a fully reusable transportation system designed to deliver more than 150 to 200 tons of payload to low Earth orbit, with launch costs driven down by rapid, repeated reuse. Compared to traditional rockets like Saturn V or even the upcoming SLS, Starship completely rewrites the scale of what's possible in size, in payload, and in capability. It's built to land vertically, be turned around quickly, and fly again closer in spirit to a commercial aircraft than a one-off space vehicle. And those aren't luxury features. They are the absolute prerequisites for sending humans to Mars. As for that 5 to 10 year timeline Musk mentioned, it's not just wishful thinking. It directly reflects Starship's development roadmap, a roadmap SpaceX has been quietly executing for years. So, How exactly does the Starship program need to evolve over the next 5 to 10 years to reach true human-to-Mars capability? To answer that, we first need to understand just how difficult a journey to Mars really is. As far back as the 1950s and 1960s, Wernher von Braun, the father of the American rocket program, was already laying out detailed plans for a human mission to Mars. In his earliest concept, Das Mars Project, developed between 1948 and 1952, he envisioned a massive fleet of 10 spacecraft, carrying a total of 70 astronauts, with tens of thousands of tons of cargo and equipment assembled in Earth orbit. By the late 1960s, those ideas were scaled down, but they were still enormous by any standard. His later plans called for a dozen astronauts in large cargo vehicles, delivering hundreds to thousands of tons to the Martian surface, with a target landing in the early 1980s, specifically around 1982, as presented in 1969. NASA itself has revisited the idea of human-Mars missions many times. One of the most influential proposals was Mars Direct, introduced in 1990 by Robert Zubrin and David Baker. It emphasized in situ resource utilization, producing return fuel directly from the Martian atmosphere, dramatically reducing launch mass, cost, and mission complexity. That was followed by NASA's Mars Design reference missions, built around Orion large surface habitats and long-duration stays on Mars. Even the Constellation program, active between 2005 and 2010, incorporated many of these elements with Mars as the long-term goal after a return to the Moon. Yet every one of these plans met the same fate cancellation or indefinite delay. The reasons were always the same: astronomical costs, immature technology, and the lack of sustained political commitment and budgetary stability. Now, compare all of that to Starship. In terms of scale alone, Starship finally matches the kind of architecture von Braun was talking about more than half a century ago. And this time, it's being developed by SpaceX, a company led by the world's wealthiest individual, where funding is no longer the primary constraint. Politically, the timing may be just as critical. The United States is now locked in an accelerating competition with China on the Moon. A system capable of reaching not only the Moon but Mars as well would send an unmistakable signal, a technological leap so large that it would fundamentally redefine the gap between the two nations. Right now, the single biggest constraint holding back Starship's path to Mars is distance. The gap between Earth and Mars can stretch to nearly 34 million miles, turning the journey into a 6 to 9 month voyage through deep space. That kind of mission pushes a crew into prolonged isolation, with communication delays stretching minutes at a time. But above all else, the greatest threat is radiation, galactic cosmic rays, and solar particle events that bombard spacecraft far beyond Earth's protective magnetic field. Low gravity, by comparison, is a manageable problem. We've already learned how to mitigate its effects through exercise systems medication and carefully designed nutrition. Radiation and exposure time, however, are far less forgiving, which is why Starship ultimately needs to reach Mars faster. To do that, the vehicle must launch with fully topped-off tanks made possible through orbital refueling. And that's not a distant 5 years away concept. SpaceX is already planning early refueling demonstrations as soon as this year, with the goal of maturing the technology by 2027. The second key factor is propulsion. The Raptor engine must continue to improve, either by increasing specific impulse thrust or both, to make faster, more efficient transfer orbits possible. Recently, Elon Musk revealed on X, "We've gone beyond 350 bar, but not safely yet. With some additional work, we should be able to achieve greater than 350 bar as standard operating pressure." That statement is widely believed to refer to Raptor 3. And looking 5 to 10 years ahead, it's not unrealistic to imagine Raptor 4 or even Raptor 5 pushing performance even further. If those upgrades come together, the implications are enormous. A Mars transit that once took 6 to 9 months could be compressed to just 3 to 5 months, dramatically reducing radiation exposure, mission risk, and the psychological toll on the crew. Of course, speed alone isn't enough. Starship also needs serious radiation protection. NASA has already shown how this can work with Orion, which uses polyethylene and water as key radiation shielding materials, two of the most effective options against galactic cosmic rays and solar particle events. The reason is simple: hydrogen-rich materials interact efficiently with protons and neutrons, slowing down secondary neutrons generated by high-energy radiation. Polyethylene, in particular, has a higher hydrogen density per unit mass than water, making it ideal for lightweight shielding layers. In real NASA designs and studies, studies, polyethylene is often used as interior linings or secondary structural elements, while water, whether stored, water wastewater, or coolant, is repurposed as a flexible water wall around crew areas. Applied to Starship, this approach becomes even more powerful. SpaceX doesn't need to reinforce the entire vehicle. Instead, shielding can be concentrated around the main habitation zones, especially the sleeping quarters where astronauts spend most of their time, and therefore receive the highest cumulative radiation dose. This is where Starship's sheer size becomes a decisive advantage. With the ability to carry hundreds of tons of payload, it can support much thicker radiation barriers, potentially on the order of 70 to 140 centimeters of water. Based on recent studies using onboard water tanks, water later produced via ISRU, or even thick polyethylene or hydrogen-rich composite structures. Unlike Orion, which carries just 4 crew members and must optimize every gram of mass Starship can afford to think in entirely different terms. It can bring tons of polyethylene or advanced hydrogen-rich materials without being constrained by weight, fundamentally changing how radiation protection for deep space missions is designed. And of course, technology on this scale doesn't come together in just 1 or 2 years. But if Musk is seriously talking about landing humans on Mars within the next 5 to 10 years, then it's very likely that much of this work is already underway behind the scenes, and that early testing may not be far off. Beyond the transit itself, approaching Mars introduces 2 additional and very different challenges. The first is landing on the Martian surface. Mars has a much thinner atmosphere than Earth, which results in lower peak entry heating, roughly 1,200 to 1,400 degrees Celsius, compared to 1,600 to 2,000 degrees during Earth re-entry. That actually makes the job of Starship's ceramic heat shield somewhat more forgiving, as long as the entry angle is carefully tuned to avoid either skipping back into space or burning up. This is not entirely new territory. SpaceX can draw on decades of experience from uncrewed Mars landers, as well as lessons learned from lunar and planetary descent profiles. From a purely thermal standpoint, Mars entry is challenging but manageable. The second problem, however, is far more difficult: getting back home. Returning to Earth depends entirely on a self-sufficient fuel supply chain on Mars. SpaceX has no intention of hauling return propellant from Earth. The mass penalty would make that approach completely impractical. Instead, the entire strategy hinges on in situ resource utilization, or ISRU. The plan is to send fully autonomous propellant production systems to Mars on the very first uncrewed Starship missions, currently targeted as early as 2026. These vehicles would carry ISRU hardware electrolyzers to split water into hydrogen and oxygen, along with either stored water or the ability to extract subsurface ice to kickstart the process. Mars's atmosphere is composed of roughly 95% carbon dioxide, providing an abundant raw material. Through the Sabatier reaction, combining atmospheric CO2 with hydrogen, methane, and oxygen can be produced as propellant. This process is extremely energy intensive. It would require large-scale power generation, either from expansive solar arrays or compact nuclear reactors, and it must operate continuously for 1 to 2 years, between launch windows which open roughly every 26 months. The goal is to accumulate on the order of 1,200 to 1,500 tons of propellant, enough for a single Starship ascent from the Martian surface. SpaceX is developing compact, highly automated ISRU modules, drawing inspiration from NASA technologies such as MOXIE aboard the Perseverance rover, which has already demonstrated successful oxygen production from Martian CO2. Once sufficient propellant is produced, Starship would lift off vertically from Mars. With gravity at just 38% of Earth's ascent, becomes far easier and significantly more fuel efficient. From there, the vehicle would enter Mars orbit, perform aero capture or retro burn maneuvers, and begin the long journey back to Earth. In a recent discussion post asking, "How valuable will the biggest company be in 10 years?" Elon Musk made a jaw-dropping claim. He casually replied, "Maybe as high as $100 trillion. That number stunned a lot of people. To put it into perspective, it's roughly 22 times the current market capitalization of NVIDIA, the most valuable public company in the world today. Musk didn't specify which company he was referring to, and that ambiguity matters. After all, he's the CEO of multiple major ventures: SpaceX, Tesla, Starlink, xAI, and more. But when you look a little deeper, the implication becomes hard to ignore. Not long ago, Musk left a telling comment that sheds light on what he really meant. He wrote, Space-based industries will vastly exceed the value of all of Earth, given that you could harness roughly 100,000 times more energy than Earth and still be using less than a millionth of the sun's energy. What Musk is pointing to here is scale a level of economic scale that simply doesn't exist on Earth. Once humanity starts building massive energy and industrial infrastructure in space and orbit on the moon, or eventually on other planets, we are no longer constrained by Earth's atmosphere geography or even the day-night cycle. Direct access to uninterrupted solar energy alone changes the equation entirely. At that point, the size of the economy isn't just larger, it becomes almost unimaginable by today's standards. And crucially, only one company is actively building the system required to make that future possible. That company is SpaceX. Starship isn't just a rocket meant to replace Falcon 9 for satellite launches. It's a multi-role space transportation platform, a launch vehicle and orbital tanker, enabling large-scale refueling in space, and the human landing system variant designed for lunar missions and beyond. In other words, Starship is the missing piece, the infrastructure layer that unlocks the large-scale space industry. This lines up almost perfectly with another bold statement Elon Musk has made about SpaceX's future. At one point he said, Starship will add 3 orders of magnitude to SpaceX mass to orbit and beyond. What Musk is communicating here becomes very clear once you look at the technical context and his long-term ambition. 3 orders of magnitude simply means a roughly 1,000 times increase because 10 cubed equals 1,000. Today, SpaceX relies on Falcon 9 and Falcon Heavy to deliver payloads to orbit. Each launch typically carries on the order of a few tens of tons to low Earth orbit. Over the course of 2025, SpaceX is estimated to have delivered roughly 1,500 to 1,600 metric tons of payload mass to orbit in total, already an industry-leading number. But Starship changes the scale entirely. Once fully operational, Starship paired with the Super Heavy booster is designed to deliver 100 to 150 tons to LEO in fully reusable mode and potentially 200 tons or more in expendable or optimized configurations. At that point, if SpaceX flies Starship at high cadence, the total annual mass delivered to orbit could reach 1.5 million tons per year. That number is hard to even wrap your head around. To put it in perspective, the entire human race across nearly 60 years of spaceflight has launched only about 45,000 to 50,000 tons of material into orbit in total. In other words, 1 year of Starship operations could deliver more than 30 times everything humanity has ever put into orbit combined. And that's the scale Musk is talking about. So, the real question isn't whether Starship is big. The question is just how enormous does Starship's operational ecosystem have to be for numbers like this to even make sense? Now let's put some real numbers on this. Imagine SpaceX operating Starship version 3, whether it's launching massive batches of Starlink satellites or even hauling entire data center class infrastructure to the moon. If you assume a fully reusable Starship configuration capable of delivering 200 tons of payload to low Earth orbit per flight, a figure Elon Musk has repeatedly floated for future. V2 and V3 designs, once upgraded, Raptor's lighter structures and full optimization are in place. You can start to calculate what this scale actually looks like in practice. Let's begin with the target roughly 1.5 million tons to orbit per year. At 200 tons per launch, that works out to 7,500 Starship launches annually. Break that down further, and you're looking at about 20 to 21 launches per day, averaged across the entire year, with a small buffer to account for maintenance weather or operational downtime. That sounds insane at first glance, but it's surprisingly consistent with Musk's long-term rhetoric. He has openly talked about thousands of Starship flights per year, and at times has even thrown out extreme figures like producing up to 10,000 Starships per year in the far future. That number isn't a literal near-term plan. It's meant to signal automotive-scale mass production, more Tesla than traditional aerospace. Crucially, SpaceX wouldn't need anywhere near 10,000 vehicles flying at once. If each Starship Super Heavy stack can fly 50 to 100 times over its operational lifetime, assuming rapid turnaround and aggressive reuse, something Falcon 9 boosters have already demonstrated with dozens of flights, then a fleet of just 75 to 150 active vehicles could theoretically sustain 7,500 launches per year through continuous rotation. The real bottleneck isn't vehicles, it's infrastructure. To support 20 launches per day, the number of launch pads would have to scale dramatically. Right now, SpaceX is on track to operate 3 Starship-capable pads in the near term, 2 at Starbase and 1 at LC-39A, with additional pads planned at SLC-37. But to sustain this kind of cadence, SpaceX would likely need at least 6 to 8 active launch pads spread across multiple sites. Each pad would need to support 1 to 2 launches per day, which implies lightning-fast propellant loading, rapid inspections, streamlined integration, and near-industrialized launch operations. At that point, Starship stops behaving like a rocket program. It starts behaving like a global logistics system, one designed not just to reach orbit, but to move mass at a scale humanity has never even attempted before. But launch cadence is only half the story. The other side of the equation, and arguably the most interesting and most difficult, is Starship production. Elon Musk has been very open about this challenge. He has repeatedly talked about building massive gigabay factories, designed to manufacture Starships at true industrial scale, explicitly inspired by Tesla's automotive production lines rather than traditional aerospace assembly. The idea is simple, but radical rockets built like cars. As of early 2026, SpaceX is targeting the production of around 10 Starship Super Heavy sets per year, with plans to ramp that up gradually to dozens and eventually hundreds per year. Realistically, reaching that level within the next decade will be extremely challenging. That said, to sustain 7,500 launches per year with very high reusability, SpaceX wouldn't need to build thousands of new vehicles annually. They would only need a few hundred Starships per year to replace worn-out vehicles and expand the fleet over time, not anything close to 10,000. However, if SpaceX truly wants to realize Musk's vision of 3 orders of magnitude growth and eventually scale toward Mars, where thousands of ships may be required per planetary launch window, then much higher production rates will become necessary. This is where SpaceX's manufacturing philosophy becomes critical. Unlike legacy aerospace, they are already applying automotive-style techniques, extensive robotic welding, large-scale 3D printing for structural and engine components, and aggressive supply chain optimization. The clearest example is Raptor. SpaceX is already producing hundreds of Raptor engines per year, something that would have been unthinkable for a full-flow stage combustion engine a decade ago. If SpaceX can push the cost of a single Starship down to a few $1,000,000 per vehicle, a target Musk has repeatedly stated aiming for, under $10 million, potentially even cheaper than a Tesla Semi, then producing hundreds of Starships per year stops being science fiction. At that point, it becomes a question of capital investment and time, not physics. Launch cadence, however, remains the biggest near-term bottleneck, especially for missions beyond Starlink. Reaching 20 launches per day requires solving several enormous challenges simultaneously. First is rapid methane and liquid oxygen fueling. Each Starship flight consumes thousands of tons of propellant, which demands massive on-site production, storage, and transfer systems operating continuously. Second is ultra-fast inspection and reuse. Falcon 9 boosters currently take weeks between flights. Starship's long-term goal is turnaround times measured in days or even hours. Then there are regulatory and operational constraints. Today, the FAA permits only 25 launches per year at Starbase. That number would need to scale to hundreds or thousands annually, which requires an unprecedented safety record. On top of that, come airspace management, maritime exclusion zones, and orbital traffic coordination, especially critical as launch rates climb. These are not minor hurdles. They are structural barriers that SpaceX must systematically dismantle if Musk's vision is to materialize. Taken together, the overall feasibility of this plan is best described as medium to high in the 2040 to 2045 timeframe, not within the next decade. Elon Musk has a well-documented habit of setting goals that sound impossible, not because he expects to hit them on schedule, but because they force organizations to move faster than they otherwise would. History backs this up. SpaceX made partial reusability with Falcon 9 routine when the industry said it was impossible. Dragon broke Russia's monopoly on crewed access to orbit, and now Starship fully reusable super heavy lift is moving steadily from concept to reality despite years of skepticism. So, while the timeline may slip, the direction is clear. What once sounded impossible has a habit of becoming inevitable at SpaceX. At the end of the day, launching satellites at truly massive scale creates an entirely new kind of strategic leverage. Countries that control synthetic fuel supply chains and launch capacity gain a powerful advantage, forcing traditional oil exporting nations to rethink their role in a rapidly shifting global energy order. More importantly, Starship fundamentally reshapes geopolitical power itself. It challenges traditional concepts of airspace sovereignty because suborbital trajectories cut through the blurred boundary between atmosphere and space, a gray zone that existing missile defense systems are poorly equipped to monitor or intercept. The U.S. military has openly expressed interest in rapid global mobility, the ability to deliver tens of tons of equipment or troops to anywhere on Earth within an hour, dramatically reducing reliance on overseas bases and aircraft carrier groups. The author argues that this represents a shift in power from horizontal expansion rooted in geography and physical presence to time dominance. In other words, whoever controls launch windows and orbital access controls strategic initiative. The United States is building a closed-loop advantage through SpaceX's civil-commercial model, integrating reusable launch vehicles, Starlink, and orbital logistics into a single ecosystem, one that could become a formidable technological barrier for competitors in the near term. In just a few days, we'll wrap up a roller coaster year of 2025, marked by 5 Starship flights from SpaceX, flights that gave us all the thrills, the nerves, and the excitement we live for. But those feelings are set to hit even harder in 2026, as this private company gears up for even bolder plans, catching both Starship and Super Heavy with Mechazilla, carrying out orbital refilling missions with Starship, and most exciting of all, landing an uncrewed HLS mission on the Moon to test and earn NASA's crew certification. All of these daring goals serve one ultimate purpose: supporting the Artemis III mission, a mission that promises to capture the world's imagination and make a global impact. It's not just about sending astronauts to the lunar surface, planting a flag, and scooping up a few buckets of regolith to bring back to Earth. This mission will lay the groundwork for an even bigger vision, one that NASA Administrator Jared Isaacman publicly shared on television.
Let's build the moon base, and then from there we're going to start making investments in nuclear power in space, nuclear propulsion, so we can make that next giant leap.
To achieve these near-impossible goals, SpaceX now has less than 2 years to get everything ready before Artemis III, originally scheduled for 2027. So, is that timeline completely insane, especially when SpaceX hasn't even rolled out a full HLS vehicle yet? Well, maybe not, but it would certainly be extremely challenging. That's exactly why President Donald Trump signed an executive order called Ensuring American Space Superiority, on the very day Jared Isaacman officially took office as NASA Administrator. Interestingly, both men are known to have a close relationship with SpaceX CEO Elon Musk. The order specifically emphasizes returning American astronauts to the lunar surface through the Artemis program in 2028 instead of 2027 to ensure feasibility and safety. Essentially, it publicly shifts Artemis III back by about a year, giving SpaceX extra time to prepare. And that's not a bad thing. After all, this mission involves astronauts' lives and the reputation of a nation. More time for SpaceX means a higher chance of success. Of course, this delay isn't just for SpaceX. It also applies to the other vehicles. The SLS and Orion for Artemis II are both in their final stages, already docked and set to launch in 2026. But the SLS and Orion for Artemis III are still in production and need extra time for thorough testing and completion. In fact, the NASA Inspector General even